Hello, everybody, and welcome to week 4 of Math 4400. So today we're going to be talking about algebraic structures and Lagrange's theorem. So the idea basically today is we're going to take some of the ideas and explorations we made last week. We're going to develop a little bit more formal language to discuss them, and then we'll be able to deepen our applications and our understanding of modular arithmetic using this more formal setup. And so this is kind of how math works in general. You explore something, you find some interesting patterns, you find some interesting ideas, but then you need to build up your language so you have the right tools and the right vocabulary to talk about the things you've discovered. And so today is sort of building up that language. So I'm going to start with a big, long definition. And okay, so it takes up the entire screen, so that looks pretty intimidating. And so this is the definition of a ring. Okay, it takes up the entire screen. We'll go over it. But I just want to say this is just what we were calling a number system last week. Now I'm going to give, last week I gave a short version of the definition. Now I just want to expand out exactly what is meant by that definition and be a little bit more precise. But this is just what we called a number system last week. So a ring is the technical term though. So we called this number system last week. What we're going to call a ring, some sources would call a commutative ring. But we won't ever talk about rings that aren't commutative. So somehow this is just a ring for us. Okay, so a ring is just a set. So a set is just a collection of things equipped with some extra structure. So there should be an addition law. So that should take in two elements of your two elements of R and spit out a new element called A plus B. And there should be a multiplication law. That's going to take out two elements of R and spit out a new one called A times B. So I usually write multiplication with a dot. And then there should be two distinguished elements inside of the ring. There should be one element you call 1, and there should be another distinguished element you call 0. And then all of this structure and these elements, they should satisfy the following rules. So your addition should satisfy the commutative and associative laws. So commutative just means it doesn't matter whether you add A plus B or B plus A, you get the same answer. So the order of addition doesn't matter. And then associative says it doesn't matter how you group terms when you're adding. So you do like parentheses, A plus B plus C. This is equal to grouping another way, like A plus B plus C. So for example, so associative is just sort of about it not mattering how you group terms when you evaluate. Okay, so that's first rule is that addition has to satisfy these standard laws. The second rule is that multiplication should also satisfy the commutative and associative laws. So same kind of thing here, except instead of adding, I would have multiplication. And then sort of A times B is going to be equal to B times A. So maybe I'll write that for commutative. Good. So these are just basically saying that addition and multiplication are going to behave the way you expect based on your experience of integers and real numbers and complex numbers and Z mod NZ. Building on that, there should also be some rule that describes how they interact, and that's the distributive law. And that just says A times B plus C is AB plus AC. Okay, so again, just what you expect to be true in a number system. We require that to hold. Okay, and then there are some special rules governing 0 and 1. So 0 and 1 are these distinguished elements, and these rules explain what's distinguished about them. So the thing about 0 is that if you have some element of your ring, and you add 0 to it, you should get the same thing back. So A plus 0 is equal to A for any element A of your ring. And then what's special at 1? Well, that's special with respect to multiplication. So A times 1 is going to be equal to A for any element of your ring. Okay, but that's what you know about 0 and 1 already. And then finally, there's something else important about addition, which is no matter what element we take in our ring, so if we have any element A of my ring, there should be some other unique element called minus a, such that if I add a together with minus a, so if I add a together with minus a, then I get 0. Okay, so this last law essentially says that not only am I allowed to add, I'm also allowed to subtract. And so notice, when we don't have an analogous law for multiplication, if we had an analogous law for multiplication, that would sort of be saying we're allowed to divide. But we already saw in examples yesterday, like the integers, you don't always want to let yourself divide. Okay, so that's the definition of ring. Again, we just called it a number system last week. And this is just spelling out the properties that we want to hold. Okay, so here are some examples. So, well, last week we talked about the integers, the rational numbers, the real numbers, the complex numbers, and Z mod NZ. Let me introduce one new example that we'll study more next time, which is if you start with some ring, so maybe you start with the integers, then you can look at the ring of all polynomials with coefficients in R, I should say, in the variable X. So we write that as R brackets X, and that just means polynomials with coefficients in R, and the variable is X. So for example, if I'm saying Z brackets X, then I'm looking at polynomials with integer coefficients like x squared plus 5 or x cubed plus x plus 1. Those are both polynomials with integer coefficients. And well, if I add those two together, well, I'll just get x cubed plus x squared plus x plus 6, which is again a polynomial with integer coefficients. So I have an addition law. And if I multiply those two polynomials together, I'll get x to the 5th plus 6x cubed plus x squared plus 5x plus 5. Hopefully I did that right, but you can FOIL that out and check. And again, this is a polynomial with integer coefficients. And if you think about it, like these rules, you can go back and check. It's a little bit painstaking, but you could check that these satisfy the associative law, the commutative law, the distributive law. It's not so bad to see that there's like, if I sort of have one polynomial, I can sort of get a minus that polynomial by sort of flipping all the coefficients to minus signs. Those add together to 0, so good. Just the sort of constant polynomial 0 is the 0 element, and the constant polynomial 1 is the sort of element 1. So this all makes sense. Good, at least when I have integers, this all makes sense. But and if you think about the rules that define this addition and multiplication, like they're sort of built out of, like we build them out here of addition and multiplication in Z, but we can build them out of addition and multiplication in any ring, and it's always going to still work out. So these rules make sense with coefficients in any ring, and that's sort of why you get a polynomial, like why this ring, so no matter where you take your coefficients, why the set really becomes a ring with these operations. Okay, so we'll talk about polynomial rings more, especially when the coefficients are in a field. So a field I'm going to define next week, but a field is something like the rational numbers, the real numbers, the complex numbers, where every non-zero element is invertible. But I'll give that definition again. Not next week, but on Thursday, or on the video for Thursday, rather. So we're going to come back to that concept. Okay. So just as an example of doing this kind of computation, we could compute x squared plus 2, where I think of that as being a polynomial, not with coefficients of integers, but I think of these coefficients as being in Z mod 3Z. So if I do that, then it's just x squared plus 2 times x squared plus 2. So I just FOIL that out. So the first term I get is x to the 4, and I get plus 2x squared plus 2x squared. So 2x squared and then 2x squared plus 2 times 2. So let me just write out sort of 2 times 2 for the constant terms, which is equal to x to the 4th plus 2x squared plus 2x squared. And then 2 times 2 is not, and 2 times 2 is not 4 because we're not working in Z, we're working in Z mod 3Z. So 2 times 2 is 1 plus 1. Okay, so that's, but okay, so you see there's no problem doing this out, and I just use, instead of using the multiplication operation in Z, I used a multiplication operation in Z mod 3Z. I still sort of get a nice answer. Okay, so the next thing I want to formalize is, again, it's something we talked about a lot last week, but now I just want to set it up in this general setting. And it's about when you can divide by an element. So if we have a ring R and we have an element A in R, then we say A is invertible, or that A has a multiplicative inverse. If there's some other element in R, which we write sort of suggestively as A inverse, such that A times A inverse is equal to 1. So such an element, if it exists, you should think of it as being sort of 1 over A. And you can, and we're not going to talk about this anymore, but you can show that there's sort of, if such an element exists, there's exactly one such element. Like you can't have two different elements such that that multiply by A to give 1. Good. And again, the point is, it's sort of convenient to let ourselves study rings where you can't necessarily divide by every element. And the elements you can divide by are those that have multiplicative inverses. So this is like what we were studying with Z mod NZ last week. So then let me just add some more notation. Again, we're just building our vocabulary so we can talk about these kinds of things more generally. So if I have a ring R, then I write R cross. So just like I wrote Z mod NZ cross last week, R cross for the set of all invertible elements in R. I think I wrote Z mod NZ cross last week. Now I actually can't remember. But okay, well, we're about to write it if I didn't write it last week. So R cross means just the set of all of the invertible elements. So, okay, so let's talk about some examples that we saw last week. So Z cross, that's all of the invertible elements in Z. And we talked about this as an example last week. The only ones are plus or minus 1. So here it's really important that when I say sort of an element is invertible in Z or has a multiplicative inverse in Z, like if that multiplicative inverse has to be an integer too. Like I can't say, like when I ask if you have a multiplicative inverse in Z, like 2 doesn't, because so even though 2 has a multiplicative inverse in the rational numbers, that's not an, like 1/2 is not an integer. So Z cross is just plus 1 and minus 1. But if I look at the real numbers, the rational numbers, or the complex numbers, then I just get that everything non-zero is invertible. So R cross is sort of everything in the real numbers that's non-zero. The invertible rational numbers, Q cross, are everything in the rational numbers that's not zero. And the invertible complex numbers are everything in the complex numbers that's not zero. That sort of fits with what you are probably familiar with. I mean, you can always divide by a non-zero element, the real numbers, rational numbers, or the complex numbers. Okay, and then last week we saw that in Z mod NZ cross, in Z mod NZ, the invertible elements sort of corresponded exactly to the elements A, where the GCD of A and N was equal to 1. So remember, Z mod NZ, I thought of as being just the symbols 0 through n minus 1. So then the addition and multiplication are defined using modular arithmetic, and then just shifting back to get between 0 and n minus 1, or between 0 and n. Good, and so then we saw the invertible ones were the ones, the invertible elements were the ones that had GCD 1 with n. So the ones that are, the elements are co-prime to n. Okay. Good, so that's what a ring is, and that just, so a ring is sort of what we called number system last week. We spelled out exactly what that means here. And then I'm just recalling this terminology, talking about multiplicative invertible elements. R cross is a set of invertible elements. And we saw it was sort of interesting to think about R cross. Like, sort of, for example, it gave you this different way to think of being co-prime. It was related to the Euclidean algorithm and so on. So this is sort of an interesting concept. And so we also want to have some theory that sort of captures the structure of R cross. And that is a theory of abelian groups. So here's another definition. So an abelian group, I'll usually just say group because we're only going to talk about abelian groups. But if you look in the book, group is something slightly more general. Good, but so an abelian group is a set A, now just with a single operation. Instead of writing it as plus or a dot, I'm going to write it as star when I sort of work in complete generality, just to emphasize that sort of maybe we don't want to think of it as being one of our previous operations because it could be something different, or it could be either one of our previous operations. Good, so it's an operation star. So I just can take two elements. I can make a new element, A star B. And there should be now just one distinguished element. So instead of having a 1 and 0, we just have a single element called the identity element, and which I write as E. Okay, and these should obey the following rules. So star should satisfy the commutative and associative laws. A star E should be equal to A for all elements in A, or for all elements. And then for any element A and A, there should be a unique element B, or sometimes we write B equals A inverse, such that A times B is the identity element. Okay, so examples. I mean, this is just basically, this looks like some subset of the structure we already considered, the structure of a ring. And really that is the case. So for example, if I take the integers and then my operation star is just addition, so it's plus, and then I take the identity element to be 0, that gives me a group. I mean, somehow the rules I wrote down here are just a part of the rules I wrote down describing a ring with addition. Okay, but so the nice thing is I can also understand the invertible elements in this way, because if I sort of take like the invertible real numbers, which is just all non-zero real numbers, and I take my operation star to be multiplication, I take E to be 1, then that also satisfies all these rules. And similarly, if I do that with Z mod n Z cross, and I take multiplication as my operation, and then identity element is just 1, that's again going to satisfy all of these rules. Good. So, and somehow this is some different set of rules describing some type of structure you can have that we could use. I mean, somehow we could either use it to study like the addition structure on addition, or to study sort of the multiplication structure, at least if we only restrict to invertible elements. Okay, and this is a powerful tool to have sort of some abstract framework for handling both these kinds of things. And it's maybe not completely clear from what I've said already that Z mod n Z cross with multiplication is an abelian group. But really it's true for any ring R. Sort of I can take sort of the whole set R and just forget about multiplication and only have addition, and that gives me an abelian group with identity being the 0 element. Or I could take the invertible elements R cross under multiplication and then take the identity element to be 1. And this also gives me an abelian group. And so like the thing that's sort of not completely obvious here and here was that if I have two elements in R cross, so that gives me that means I just have two elements A and B of R, both of which have inverses, then you need to check that A times B also has an inverse. That's sort of the key thing to check, because otherwise this might not be, this multiplication operation wouldn't make sense, because you could take, somehow the operation wouldn't make sense if you could take two invertible elements in R and multiply them together, and what you got wasn't invertible anymore. Because I mean, we need to stay in this world for it to be an abelian group. But it's easy to check. I mean, if A has an inverse and B has an inverse, well, then the product AB also has an inverse, and it's just B inverse times A inverse. So if I just expand out AB times B inverse A inverse, sort of first I'd kill this, and then I'd cancel these, and I just get 1. Okay, so that's a source of abelian groups, and good. And so what we're going to want to do is then use like the general abstract frameworks of abelian groups to say something that's useful in these specific examples that we're interested in. Okay, and so we're going to make our way towards that. We need another piece of notation beforehand. So if I have a group A, then the order of A, which I write sort of like absolute value sign A, it's just the number of elements in that group A. So for example, the integers have infinitely many elements. So if I ever have infinitely many elements, I just write infinity, and if that's a case that won't be so interesting to us. So this is the integers under addition. But if I look at the integers under multiplication, which remember, or sorry, the invertible elements in the integers under multiplication. So z cross just meant plus or minus 1, the set of invertible elements in the integers. Well, plus 1 is an element and minus 1 is an element. So there are two things there. So the size of z cross is 2. The size of z mod nz, so here this is a group under addition. Is n, and if I take the numbers 0 up to n minus 1, I have n of those. And then more interestingly, we saw last week that if I take the set of invertible elements in z mod nz, so the set of elements that have multiplicative inverses here, we saw that's the same as the number of elements. Let me say it in a different way. I mean, being an element in z mod nz is in z mod nz cross, or it has a multiplicative inverse, if only if its GCD with n is 1. So I already mentioned that once today. And so the size of this group, z mod nz cross, is just the number of a between 0. Maybe I should write this. So it's the number of a between 0 and n that have GCD 1 with n. Good, so we call that number phi of n. So this is called Euler's phi function. And so phi of n is just defined to be the number of a between 0 and n minus 1, so 0 less than equal to a and less than n, that are co-prime with n, or have GCD 1 with n. And that's equal, another way to think about that is that's just equal to the order of this group, z mod nz cross. Okay, so just as an example of that, well, if p is a prime number, then every non-zero number less than it is co-prime to it. So that means, well, how many non-zero numbers are there less than p? There are p minus 1. So just like, so z mod pz cross, this is 1, 2, up to p minus 1. So there are, phi of p is p minus 1, which is the size of this group. Okay, so good. Now we come to like something interesting. So this is Lagrange's theorem, and it's a theorem that holds for any finite group. And in class, we're going to see that it has some really interesting consequences when we apply it to like z mod nz cross. But somehow it's nice to state it and think about how to prove it, just talking about any finite group, because that isolates and sort of points and emphasizes exactly the structure we're using, instead of sort of having all this extra structure floating around that sort of confuses things. Okay, so what Lagrange's theorem says is if I have any finite group A, so finite group just means the order is the finite number. So I'll write the order of this group as n, so the number of elements in the group is n. Then if I take some element of this group and I raise it to the nth power, I get the identity element. So raising it to the nth power here just means I apply the group operation n times. So for example, like, yeah, maybe I'll say that, I'll leave it at that. So raising to the nth power just means apply the group operation n times. So in z mod nz cross, that's literally raising to the nth power, or like r cross in general, that's raising to the nth power. If you take like the integers under addition, this would just mean multiplying by n. But usually when we're writing in general, we sort of write with this multiplicative notation instead of the this like exponential notation instead of like writing n times a. Okay, but the point is, there's some number such that when we raise a to that number, we get the identity element, no matter which element of the group I take to start with. Okay, so right, so just an example. What does this say in the specific case of? I wrote the wrong group down here. If I think about what this says in the specific case of z mod pz cross, where p is a prime number, well, that's going to be something called Fermat's little theorem, which I can reinterpret as saying, if P is prime, and then I take some A such that the GCD of A and P is equal to 1, then A to the P minus 1 is congruent to 1 mod P. So here the point is that sort of P minus 1 is equal to phi of P is equal to the order of Z mod PZ cross. So Lagrange's theorem tells me that in Z mod PZ cross, if I raise any element to the P minus first power, I get 1. And well, sort of, if I think of that instead of in terms of congruences, then this is how you write that. Another way this often gets written is that instead A to the P is congruent to A mod P. And so I get this equation just by multiplying this equation by A. Okay, good. So this, somehow the nice part about this equation, this is true when A is equal to 0 as well. So this is also true when, so this one's also true when P divides A, which is why sometimes people prefer this expression. But somehow the key part, and that's sort of easy to see, because when P divides A, both sides are 0. So the interesting case is when P doesn't divide A, I think when the GCD is 1, and then this statement is really equivalent to Lagrange's theorem applied to Z mod PZ cross. Okay, so just completely concretely, like if P equals 5, we can just check this. So if I take 1 to the 4, that's equal to 1, which is congruent to 1 mod 5. You can take 2 to the 4, that's equal to 16, which is congruent to 1 mod 5, good. I can take 3 to the 4, that's equal to 81. 81 is congruent to 1 mod 5, good. And I can take, 4 to the 4, that's 256. And again, that's congruent to 1 mod 5. Good. So that checks out for sort of Z mod 5Z. Okay, so how do you prove Lagrange's theorem? So I'll just sketch that proof. So let me just take A in A, and we call the order of A is equal to n. Right, and then so first step. So I claim there is some k greater than 0 such that A to the k is equal to 1. So how do I justify this claim? If I just look at all powers, so look at a squared, a cubed, a fourth, and so on, I go on forever. This is a list of infinitely many things. Okay, this is sort of an infinite list. Sort of by each thing, so each thing on the list is in the finite set. A, so that means sort of 2 of them have to be the same. So there's sort of A to the K1 is equal to A to the K2 for some K2 that's greater than K1. Why do 2 of these things have to be the same? Well, you can just think like if you flipped a coin sort of infinitely many times, or even if you flipped a coin 1,000,000 times, or if you flipped a coin 3 times, sort of in any of those cases, you would have to have gotten heads twice or gotten tails twice. You might have gotten only heads, so you got heads forever. or you might have gone only tails, so then you got tails forever, but there's no way you got heads exactly once and tails exactly once, because then you'd only have done 2 flips. So sort of if you've done more than 2 flips, you have to have gotten one of heads or one of tails 2 times. And this is sort of just some generalization that means sort of whenever I have a finite set of objects, if I sort of have an infinite list, or even sort of like if I have n things, I have a list of n+1 things that all live in that set, then like I have to have repeated some element. So this is called the pigeonhole principle. Good, but so I have this. Okay, and so then, well, if a to the k1 is equal to a to the k2, then I can multiply by a inverse. So I get sort of a1 to the k1 times a inverse to the k1 is equal to a to the k2 times a inverse to the k1. And then, well, a inverse to the k1 times a1 to the k1, that just cancels. So I just get the identity element. And here I get a to the k2 minus k1. And k2 minus k1 is some positive number because I took k2 to be greater than k1, so I win. So that verifies the claim. So that's the first part. There, I found some k such that a to the k is equal to 1. Okay, so now let me sort of take the smallest such k. Then the numbers the numbers 1, a, and so on, 1, a squared, all the way up to a to the k minus 1 are distinct. So not the numbers, but the elements. Of a. Okay, so I'm just gonna make myself some more space. So that's gonna take me a second. Okay, so I have this distinct elements of a. So these are k distinct elements. Somehow, because if they weren't distinct, then I'd have sort of 2 of them. They're the same, and I do the same trick, and I get that a to their difference was equal to 1. Okay. Good. So that would give me some smaller k. So I have 1 through a to the k minus 1. These are k distinct elements of a. And so, well, if this is everything, then k is equal to n. And so in particular, so a to the n is equal to 1. And otherwise, sort of take some other element x and look at, so okay, so first I have this table, this part, and I add another sort of column. I may make a table. And so I claim these are all distinct. So, I mean, if I already saw these guys are all distinct. If any 2 of these guys are the same, well, then I just multiply by x inverse on the left, and I'll sort of get 2 things in here that are the same. So definitely everything here is different. So I just need to see sort of x times a to the I is not equal to, I need to see I don't sort of have any overlap between these 2 rows. So I need x to a to the I is not equal to a to the j for sort of any I and j up there. And this is easy. Just multiply and So, and if it's held, like if x theta I is equal to a to the j, then x is equal to a to the j minus I, just by multiplying by a to the minus I, or multiplying by a inverse I times. But that sort of contradicts what we assumed, because we assumed x wasn't a power of a. And when I do this table, I'm really hitting all of the powers of a. So good. So I haven't sort of somehow x can't be such a power. Can't happen. So you sort of keep going. And you get a table, sort of 1a squared, a to the k minus 1. Then I added an x, so xa squared, x a to the k minus 1. Sort of, then I'd sort of add in sort of y. If I hadn't hit everything yet, I'd add in y and then all those products, and these would all give me different things, and so on. So I end up with, and I'll keep on doing this till I get everything. In A. And well, I'm going to have some number of rows, and each row has k elements. So I get sort of A, the order of A is going to be the number of elements. So that's what I called n, is just the number of rows times k. So let me just call this, let me write r times k. So r is the number of rows. But then, sorry to cram this in here. I get a to the n, which is a to the rk. Then sort of standard thing applies, like this is a to the k to the r, which is 1 to the r, which is equal to 1, or e to the r, equal to e. So e is the identity element. Good, and that's what I wanted to see. I wanted to show that if I raised a to the nth power, where n is the order of the group, then I got the identity. So that's the proof of Lagrange's theorem. Good. So I want to point out that in general, if I have Lagrange's theorem in Z mod NZ, so we sort of saw this specific example like in Z mod PZ. This was Fermat's little theorem. It gave you some fun identity. In general, if I apply Lagrange in Z mod NZ cross, then I can think of that as saying that sort of for any number a that's co-prime to n, then a to the phi of n is congruent to 1 mod n. Now remember, phi of n is the number of elements less than n, the number of numbers less than n that have GCD, that are co-prime to n, have GCD 1 with n. Okay, so we'll see many examples of how this is useful in the worksheet, but somehow for this to be really useful, you need to know what this number phi of n is. So it's useful to combine with this following theorem, which says, well, if p is prime and k is a positive integer, then phi of p to the k is just p to the k minus p to the k minus 1. So this is a pretty simple thing to count. Just count the number of integers less than p to the k, a prime power, that are co-prime to p to the k. That's an exercise in the worksheet. And then the next thing is, if you have a bunch of co-prime integers, and you take sort of phi of their product, and it's just the same as the product of sort of the phis. So combining these two facts, you can compute sort of phi of n for any n in a fairly straightforward way. And we'll use this a lot on the worksheet. And so sort of giving a justification to this theorem is exercise 1 on the worksheet. So we'll talk about that more in class. And I will see you there. Thanks.